Today we're going to be discussing orbitals, and orbitals are a way of defining electron location. Where are the electrons in the atom? In order to better understand this, we're going to tell a quick story. So let's suppose we're at a baseball/softball game, and we're watching this game from the stands. The only bad thing about this field, because we had a very tight budget, is that there is a wall in front of all the fans. But the good news is that even though there's a wall in front of the fans right here and here, there's a little window in front of every seat that opens for 10 seconds, so you could see the game for 1 second as you're watching it. And then they close, and 10 seconds later it opens again. So you first start to watch the shortstop. You see the shortstop here, 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 catching a ball over here, here, here. Then you look at the pitcher. Pitcher's winding up, there, 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 talking to the catcher, there, there, there. Then you look in the dugout for the coach, pacing nervously, back and forth in the dugout, just pacing. Lastly, you look at the first baseman, here, 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 catching a foul ball, there, there. So as you're watching the game, you're going to realize that you never really know where any player is, but if you're looking for the shortstop's probably in this area. Looking for the pitcher, probably in this area. Looking in the dugout, you'll see the coach pacing around. And looking for the first baseman, you'll see the first baseman right there. So it's interesting to note that in a baseball game, if the shortstop moved over and was right here, it would not make the shortstop a pitcher. Okay, or if the pitcher were in this zone right here, it doesn't mean that the pitcher becomes the first baseman. The players are always playing their positions, and they're in their zones probably because that's what position they play. If the shortstop goes out of the zone for a while, they're going to come back in. Same thing with the pitcher, dugout, and first base. So just like a player in a baseball game or a softball game has a position, so electrons also have positions. And if you paid attention to the story, shortstop, pitcher, dugout, first base, that also corresponds to what we call orbitals, S, P, D, and F, which are the same letters as shortstop, pitcher, dugout, first base. It helps you to understand the 4 different zones that an electron can be in. An s orbital has this shape. It looks like a ball. So what you would have is the nucleus in the middle of this ball, and an electron in an s orbital would be anywhere in this region of a ball around the nucleus. Let's say this represents a 1s. Okay, this is about the size of a golf ball. Then a 2s, let's say, would be the size of a tennis ball. And then a 3s would be the size, let's say, of a softball. And they would just get larger and larger, but they would have this shape of an s orbital. The next orbital is a p orbital. This is a single p orbital. It has a nucleus going to be right in the middle, and then it's going to have 2 lobes, one on each side. And this comes in sets of 3, remember? So there's one in the x direction, there's one in the y direction, and then there's going to be one in the z direction that's going in and coming out of the screen. So p orbitals come in sets of 3 per energy level, whereas s orbitals come in sets of 1. Then recall that we have d orbitals. D's come in sets of 5. So this is a single d orbital, a single one. It has 4 lobes to it, 1, 2, 3, 4, but this is a single d orbital. They come in sets of 5. So you're going to have actually 4 of these and 1 of these. Okay, so how do the 4 of these work? Well, one of them, let's say, is going to be oriented this way. One of them is going to be oriented this way. One of them is going to be oriented this way. One of them is going to be oriented that way. And then this is the last one that's oriented vertically. So those are d orbitals. F orbitals we actually don't even have any models for. I don't even think your book has pictures of them. But these are the shapes of the orbitals. So now we know the shapes of the orbitals, that the s orbital is going to be like a sphere or a ball. P is like a peanut shape, like this. The d's, remember, had a set of 4 lobes, and 4 of them are going to look like that, and one of them is going to look like this. And then the F's, we don't really have shapes for those. So each of these orbitals is going to hold 2 electrons. Those are like the arrows that we learned in previously. Each level has certain of these orbitals. So you could see that level 1 only has S. Level 2 has S and P. Level 3 has S, P, and D. Okay, and then there's a possible number in each level, which we know that S's come in sets of 1, P's come in sets of 3, D's come in sets of 5s, F's come in sets of 7s. These are like the blanks. So you had 1 blank for an S, 3 blanks for a P, 5 blanks for a D, 7 blanks for an F. So each of the blanks represents one orbital. So this, the 1 blank represents the S, which was pictured over here. Then there's 3 blanks for the P. Remember, 1 goes in the X, 1 goes in the Y, 1 comes out at U and the Z. Then the D's, there were 4 that looked like this and 1 looked like that. Those are the 5 blanks. And then the F's come in sets of 7, and those are the blanks as well. So now we're going to talk about how many orbitals you could have in any energy level. So if you're going to talk about S orbitals, in level 1, there's only 1 orbital. Remember, there's like 1 blank for the S. And then for the 2, remember that the S has 1 blank, or orbital, and the P's have 3. So 1 plus 3 is going to make 4. Okay, then this one's going to have 1 plus 3 plus 5. That's going to equal 9. Now let's talk about the number of electrons. How many arrows could you put in each of these blanks? So 1 blank could have 2 electrons. 4 blanks could have 8 arrows, or 8 electrons. 9 could hold 18 electrons. So you could hopefully see the relationship that n squared is the number of orbitals. So if you have energy level 1, then you could have up to only 1 orbital. If you have energy level 2, you could have 4 orbitals. If you have energy level 3, you could have up to 9 orbitals. This actually continues to carry on even for elements that don't use all the orbitals. So we learned about S, P, D, and F. Technically, there's actually a G orbital, an H orbital, an I orbital. These are all theoreticals because no elements really use these. We're pretty much cutting off at the F's right now for all the elements that we know about. But theoretically, you could have more. So level 4 would have possibly 16 orbitals that hold 32 electrons. Level 5 would have 25 possible orbitals that hold 50 electrons. And then level 6 could have 36 electrons, which holds 72. Again, these are all theoretical, but you should know that those are possibilities. So now what we're going to do is we're going to take a look at the periodic table and remember what we learned already, that there are different zones in the periodic table for the electrons filling. So we know that this is filling in S, these are filling in P, these are filling in D, these are filling in F. And remember that S starts with level 1, P starts with level 2, D starts with level 3, and F starts with level 4. So all you need to memorize is 1, 2, 3, 4, S, P, D, F, and you're going to know the entire order of the periodic table. Now we're going to take a look at the energy level diagram and apply the vocabulary that we haven't learned yet. Remember when we did sulfur, we put 16 electrons into this. We went first to the 1s, then the 2s, and then the 2p. What we were doing is applying what's called the Aufbau principle. So the Aufbau principle says that you go up in order. It's actually the German word for order. So you occupy each orbital of the same energy before moving up. So we finished the 1s, then we move to the 2s. When we finish the 2s, then we move to the 2p. We don't move on to the 3s until we finish the 2p. Okay, next we're going to apply Hund's rule. You can remember Hund says 1, 1, 1. You're going to maximize the number of unpaired electrons, and that's due to repulsion. So remember that electrons represent, or arrows represent electrons. Electrons are all negative. So let's take a quick story of the school bus, just to remind you. So let's say it's the first day of school, and you have to ride the school bus. You get on the bus, and there are 3 empty seats. So you sit in the first empty seat right here. Now there are 2, and each seat holds 2 people. So now a stranger comes on the bus. You don't know this person. They're going to sit in a different seat, in a different bench. They're not going to sit right next to you. That would be pretty awkward if a stranger just sat next to you when there were empty seats. So that person who's a stranger is going to sit in that seat by him or herself or herself. Then the third person who comes on is also going to take an empty bench, and they have their own bench. Now, when the fourth stranger comes on the bus, the fourth stranger will sit with you, and that's not so awkward because there's no other seats. So, but there's going to be a little bit of, let's say, tension over here because, it's a little strange. You're sitting next to a stranger. That's repulsion. Okay, electrons repel each other, so they're going to spread out into empty orbitals. Then when they have to, they're going to double up in the orbitals rather than go to the next energy level or next set of orbitals. So that's called Hund's rule. And then we're going to lastly talk about Pauli exclusion principle. Pauli's exclusion principle says that the better way to look at it is this, which says only two opposite spin electrons per orbital. So you see how we point an electron up and we point an electron down. The electrons are spinning in the air because remember, this is all happening in 3 dimensions. So basically one electron is spinning this way clockwise and one electron is spinning counterclockwise, and that represents the up and down arrows. So when we're doing sulfur, we're going to finish up to 16. That was 10, 11, 12. And we're going to go 13, 14, 15, 16. So these are the 3 principles that we already knew these rules. Now we have the vocabulary to go with it. And recall what we did with detailed configuration, where we're going to look at the p orbitals and see how the 2 p's are 2, 2, and 2 in the x, y, and z. But here in the x, y, z, you could see that you have 2, 1, and 1, and that's going to be here 3px2, 3py1, 3pz1. That's called the detailed. And remember that you can use noble gas configuration, so find a noble gas before the element. Neon is the noble gas before sulfur. Now when you look at the periodic table, you could tell that neon ends in 2p6, so then you're just going to continue after 2p6 with a 3s2 and 3p4 to represent sulfur, because the noble gas configuration for neon is going to end right over here. So neon ends right here, and then you would take past it would be 3s2, 3p4. Now we're on page 5, and we're going to find out how do electrons relate to light, because it seems like completely different things. We talked about electrons and then we talked about light. So here is a diagram representing energy levels of an atom. Okay, you've probably seen this earlier in middle school where you've seen these circles going around the nucleus. This does not represent the fact that the electrons go around in circles as the planets orbit the sun. That was actually the idea of Niels Bohr, which today we don't agree with that theory, but we do agree that there are energy levels. So this would be energy level 1, that's what n equals 1. N equals 2 is energy level 2, 3, 4, etc. So level 1 represents the 1s. Level 2 represents the 2s and the 2p. Level 3 represents the s, p, and d. It doesn't represent that it goes in a circle, it just represents a level. The higher the level, the farther away the electrons are. So if we just consider s orbitals, remember I said like golf ball, tennis ball, softball. So the electrons would be closer to the nucleus in level 1, farther in level 2, etc. Whether you're an s orbital or a p orbital or any of them. So every level has a certain energy. You could find the energy of a level with the equation written right here. Okay, we're not going to go crazy with this. We're not going to take time to figure it out. But you could use that equation right there and then find the level energy of 6, 5, 4, 3, 2, and 1. Okay, just understand qualitatively that that corresponds to different energies. Now, let's revisit what happened with the light. When you saw the hydrogen spectrum, you saw a red line, a teal, and there was a blue and a violet, which might not have been easy to see, but technically there was a violet, a blue, a tealish green, and a red. Now we learned earlier that red has the longest wavelength, and the blue and violet side have very short wavelengths of the visible light. So you could see that the more energy is going to be the blue side. Okay, this is more energy, and the red side is less energy. Now the interesting thing is that when you plug in the tube that we saw and you look at the light given off, it's because what you're doing is you're making the electrons jump from one energy level to another. So let's talk about hydrogen, which is the easiest one to understand. Hydrogen has a 1s electron. That's all it has. Okay, if you give it lots of energy, you can make it jump up into a 2s. So the electron moves up there. So when you do that, you absorb energy. It absorbs energy to do that. However, that electron is then going to want to go back. And when it does that, it will release energy. And when it releases energy, it releases a specific amount of energy that corresponds to a frequency, which corresponds to a wavelength, which corresponds to a color. So what's really interesting about hydrogen is when the electron falls from level 3 to level 2, so this transition here is represented by this transition here, same thing. When it falls from level 3 to level 2, it gives off energy. And that energy has a wavelength. And that energy, let's say, is the red wavelength. So then you see a red colored line on the spectrum. Okay? But it also can fall from level 4 to level 2. So 4 to 2 is also a transition, but that has more energy, so you're going to see a greenish blue line. But let's say the electron falls from level 5 to 2, then it's going to give off this blue line, which is more energy still, and then when it falls from 6 to 2, it's going to give off a purple line, which has the most energy out of all the visible light. So whenever you have an electron that falls to level 2, that's going to be visible light. You can see that. However, when it falls to level 1, that's more energy than visible, because when it falls from, let's say, a level 3 to level 1, that's more energy than level 3 to level 2. You can't actually see that light, and that light is more energy than visible, which is ultraviolet. And then if it falls to level 3 only, that's less energy than visible. That's going to be infrared. So what you need to understand is that electron energy levels have specific amounts of energy. When you give electrons energy, you excite them to higher levels. That's called an excited state. And then when they come back down, they're releasing energy and they go back to their ground state. And when they release that energy, it has a certain frequency, which has a certain wavelength, which can have a certain color. And if you have a small difference, that's going to be a light of color that has small energy. If it's a big difference, it's going to have a light that has a higher energy. So that's the qualitative understanding you need to have. And then this diagram actually tells you the nanometers of the wavelength of light corresponding to each of the transitions. So you could see once again that the going to level 1, which is the Lyman series, is going to release ultraviolet light. The Balmer series is when it falls to level 2, that's going to be the visible light. And then the Passion series is when it falls to level 3, and that's going to be infrared light. And of course, we can only see the visible light. So as we move up in this page, we could see all that we learned has to do with electrons. And these, again, are the wavelengths of the light that you have for the different colors. And quantization means that energy of an electron can only have certain distinct values. So the electron must have energy level 1 or 2 or 3. There's no in-betweens, kind of like a bookshelf. You have to have a bookshelf on this, a book on this shelf or this shelf. The book is not going to be in between the shelves. So that's the same thing. Electrons have to be those specific energies. So when an electron falls from level 3 to level 2, instantly it changes from this energy to this energy. It's not like it transitions in energy. It's like an instantaneous change, and that's what quantization is.